Hi, I'm Rania Oueslati. I'm a PhD student at the University of Tennessee, Knoxville. My PhD is in electrical engineering, and the aim of my research is to design and develop lab-on-chip and readout systems for biosensing detection. And we want them to be low-cost, portable, very efficient, and innovative. For that purpose, our group came up with this palm-sized biosensor called ABC Biosensor. ACEK-based capacitive biosensor uses technology called ACEK, alternating current electrokinetics, which is a way of manipulating particles through the application of an electric field. This technology uses microelectrodes, chip sensors, to directly detect very minute levels of specific analyte from complex sample, and therefore it is more sensitive and significantly faster than traditional detection methods. So if we open this small box, we see this small PCB design that is mainly composed of ICs, impedance analyzers, some amplifiers to amplify our signal, noise filters, and obviously microcontroller to handle all those tasks. So this board requires software and hardware design. Simply by loading sample into the chip, results will be ready within 2 minutes. So our sensing is called capacitive because those microelectrodes, when immersed into liquid electrolyte, a layer of counter-ion will be formed on the electrode-electrolyte interface, which is known as the electrical double layer. The layer of the counter-ion and the electrode form the two plates in a capacitor with a separation distance of debye length, and it can be determined or manipulated by the fluid's conductivity. So we prepare our electrode by coating it with antigen molecule that they are extracted from infection agent. Those antigen will act as the probe molecule and bind to antibodies that occur in the patient samples as response to the infection presence in his body. When the antigen and the antibody bind together, the interfacial layer of our capacitor or our sensor will change. When the change occurs, then we can say whether or not the infection is present in the patient sample. The normalized change in the measured capacitance is employed to correlate with the deposition of target molecule on the surface, not the interference molecule on the surface. So in our first test, by getting the best results by the ACEK effects, we select the specific frequency and the specific voltage, and we apply our sweep time, and by loading on our electrode surface samples that they don't include our target molecule. So the sample we are loading on the surface electrode on our first test has only interference molecule. The results we need to see or to predict is a very small slope of the capacitance values versus time. When I say small, means like something less than 0.1%. We start sampling our test in sweeping time with around 20 seconds. And then when we calculate the slope, as we can see here, the slope it's minus 0.02%, which means for 20 seconds the capacitance is changing with only 0.002%. This change is too small, and we definitely can tell that the patient doesn't have the disease or the infection on this sample. Our second test, what we will do is we're going to change the sample loaded on the electrode surface, and we will have sample that it has our target molecule. The slope needs to be higher compared to the first negative testing. So by selecting that sample, loading it to the surface of the electrode, we do the same thing like with a specific voltage and specific frequency to maximize the effect of the ACEK. and we start sampling our test for 20 seconds, we see that the slope, it is minus 1.42%. This is for only 20 seconds. So when we see the interfacial layer of our capacitance is increasing, and then the overall capacitance is decreasing, and that's why we see that negative sign on our slope curve.